So with that, let's begin. So pressure introduction. So pressure, what is pressure? One of the most commonly measured and visible quantities in the industrial automation space. Other important quantities such as temperature, flow, and humidity are all derived from pressure. So essentially it's a measure of force per unit area. As this area decreases or the force increases, the pressure increases as a result. Now I'm going to get to some of the different pressure reference standards available. So gauge, absolute, vacuum, and differential. So gauge pressure uses atmospheric pressure or pressure at the sea level as its reference. It can be either negative or positive when using this reference. Absolute pressure uses perfect zero or perfect vacuum as its reference. So absolute pressure is always measured as a positive quantity. The vacuum also uses perfect vacuum as its reference and measures atmospheric pressure at the maximum level. And finally, the topic of discussion today, differential pressure references. So these actually have measured two quantities and take the difference of the high and the low pressure. Here's some of the physical representations of the different types of pressure transmitters available. So the top row are the flanged type pressure transmitters. As I mentioned earlier, differential pressure requires two inputs. So differential pressures are most likely going to be flanged. Absolute and gauge can be either. So the bottom row are actually are called inline transmitters, so they have a single input. Now I'm going to get to some of the pressure sensor technologies. So pressure sensors come in three different types: capacitance, piezoresistive, and silicon resonant. Capacitive sensors typically use a thin diaphragm. Applied pressure causes the capacitance to change, typically in the order of several picofarads. Piezoresistive or piezoresistive integrated semiconductor pressure sensors utilize a Wheatstone bridge that measures applied stress as a function of the change in the resistance of the legs of the Wheatstone bridge. And then finally, silicon resonant sensors, which are used in Yokogawa's differential pressure transmitters. These are constructed of two H bridges that resonate at 90 kilohertz. Here's a more in-depth diagram. So as pressure is applied to this silicon resonant sensor, one of the H bridges goes into tension and the other one goes into compression. So when differential pressure is applied, as seen in the diagram on the right, on the high pressure side, you have the outer tension, or outer sensor and the inner sensor. The outer sensor goes into tension, and the frequency increases above this 90 kilohertz resonant frequency. The inner sensor goes into compression, and the frequency decreases below this. And this change in frequency is proportional to the applied pressure. So as you can see in the graph at the bottom, pressure as a percentage of URL, which is upper range limit, that's the theoretical maximum that a transmitter can measure. I'll get to that in a little bit later. So as you increase this URL, you see that the outer sensor and the inner sensor gradually move apart in different directions of frequencies, and this change in frequency is proportional to a change in applied pressure. So some of the advantages of silicon resonant sensors over the other two types discussed earlier. So there's lower temperature effects and better signal-to-noise ratio at digital output and a stable signal, fewer analog-to-digital conversion errors, as well as minimal hysteresis. Next, I'm going to get to transmitter overview. So a transmitter, and in this case a pressure transmitter, is a device that has a sensor that accurately responds to a process variable, which in this case is pressure. The sensor then outputs a signal, which is then sent to an analog to digital converter, which is then amplified and sent to either a distributed control system or some other type of controller. The sensor's job is to convert this process variable into something that can be measured by electrical instrumentation, so current, voltage, resistance. Now, I'm going to go over some of the industry standard terminology for pressure transmitters, but a lot of this also applies to other types of transmitters as well. So you have the LRL and URL, which is the lower range limit and the upper range limit. So this is the theoretical minimum and maximum that a pressure sensor or transmitter is designed to measure. The range is then taken as the absolute sum of the URL and the LRL. Now, in addition to this, we also have the LRV and URV. And this is the actual range that the transmitter is scaled or trimmed to operate and measure around. Sometimes this could be the absolute extremes, but most of the times this is not the case. As seen in the diagram at the bottom, it is quite a bit less. So this is where the transmitter is scaled and designed to output its minimum and maximum current. So 4 to 20 milliamps is quite common in process control. So at 20 milliamps, the transmitter is reading the URV. At 40 milliamps, it's reading the LRV. The span is then the difference between the URV and the LRV. Next, I'm going to go over some of the basics of verification and calibration. So before we get to any discussion on calibration, it's important to understand the difference between sensors and calibrators. So sensors, similar to pressure transmitters, are devices which convert physical phenomena, such as pressure, current, voltage or temperature, etc., into a quantity that can be measured by a process control system. So some examples of field sensors include thermocouples and RTDs, current transformers, microphones, and photodiodes. So each sensor is unique. And what does that mean? That means that you can have two sensors from the same manufacturer rated for the same pressure or temperature. However, the response of that sensor will be different between individual sensor types. And each sensor will have a unique characterization curve in response to an applied stimulus. So the goal of any kind of equipment maintenance or sensor maintenance is to make sure that this curve is standardized across different sensor types. So sensor readings and scaling. So most, if not all, transmitters have default factory settings that may or may not be matched to the quantities they are measuring. The idea here is to linearize the process variable across the transmitter's full span. So for example, if we have a pressure sensor rated for 2000 psi, we want it to output maximum current when we apply that pressure to the input. For this discussion, for the remainder of this discussion, we will focus on pressure sensors. Other quantities can all be derived from pressure. The next class of instruments I want to go over are calibrators. So calibrators combine accuracy with portability. Especially for in-field usage, they are most likely to be battery powered. They usually support the standard industrial protocols such as heart, brain, and Profibus. And other features also include data logging to internal or external memory. So calibrators sound very similar to sensors, and that is true to a large extent. So why would you use a calibrator, and what is the purpose of a calibrator? So a calibrator is a type of instrument that functions both as a source and syncing device. Similar to sensors, they can measure temperature, voltage, etc., as well as source those quantities. So their main function is to verify sensor output by producing a stimulus, either current or voltage, and then verify the reading of the transducer. So an example would be if a technician would want to verify their temperature controller is displaying the proper output based on a certain thermocouple type, they would then use a temperature calibrator. So as seen at the bottom, on the right side of the diagram is the temperature controller, and on the left side is a temperature calibrator. So a temperature calibrator is essentially a high precision DC voltage source that's designed to output a range of voltages that correspond to different thermocouple types. The technician would then use the calibrator's output to verify and adjust the sensitivity of this controller to see if it's matching up with what the calibrator is outputting. So, after going over some of the basics of calibration, why is calibration important? Why is it such a commonly used term, and what's the rationale or purpose behind it? So, all test and measurement devices, which include field transmitters and field equipment, come with certain accuracies as per specifications. However, due to the environments they are exposed to or age of being out in the field, these instruments are prone to wear and tear and degrade over time. Therefore, some kind of periodic maintenance is necessary, anywhere from monthly to annually, to make sure these instruments maintain their integrity. And thus, at its core, calibration involves adjusting the tolerance levels of a measuring device against a known reference so the two are in sync. So when we get to calibration, we come across two commonly used and probably commonly heard terms before: as found and as left calibration. These are the types of calibration data available to manufacturers and end users of field instruments. So as found calibration refers to the performance of the device in its latest state, either from the field, being out in the field for many years, or being commissioned straight from the factory. And as found tests usually involve checking the linearity of a transmitter across at least 2 points in either direction. So the 0, 100% point, 0, 50, or 100% point, and back down from 100% to 50% to check the hysteresis. If the device passes as found testing, no further action is necessary. However, if any one or more tests fail, then adjustments would be the next step. Adjustment involves using a known reference, which in this case would be a calibrator, with a transmitter, and essentially adjusting the values in the transmitter so that they are properly aligned with the pressure that they're measuring. Once this adjustment phase is finished, then the as left test is the next step. And as left test could be very similar to the as found test, or it could test other things, but as far as keeping the information standard, you generally want to run the same tests you ran in your as found tests. Another very important point is calibration versus verification. So although the terms are used interchangeably, they are different processes. So calibration is used to determine what correction is needed to offset on an instrument to meet its specifications. Verification, on the other hand, determines the percentage error of the instrument's readings relative to a maximum percentage that the end user is willing to accept. So, for example, if there's a 1% error tolerance specified, and testing reveals that there's a 2% error, the verification would result in a no pass. So, pressure transmitter verification will involve about 4 steps, which I'll discuss in a moment. first step would be to choosing a span. So going back to our earlier discussions on the pressure transmitter, the span is a subset of the maximum range that is used to linearize the transmitter and decide what pressure range that transmitter is ideally set to be useful. So this is the URV minus the LRV. Linearization then involves making sure that the transmitter is outputting the 4 to 20 milliamp range across the span. The second part of verification involves comparing the measured value of a transmitter against a trusted source. So in this case would be a pressure calibrator. General rule of thumb in calibration metrology is that you need to have a calibrator which is at least 4 times as accurate as the unit under test. So in our example, if we're using a transmitter rated for 0.04% of reading, we want a pressure calibrator that is at least as accurate as a 0.01% class. Once we choose this calibrator, the next step would be performing an as-found calibration. And part of that involves choosing tolerance levels. So tolerance levels are the degree to which pass or fail is determined. So different manufacturers have this calculated in different ways, or at least have this reflected in different ways. The way Yokogawa does this is plus or minus of the 100% value of your measurement function minus the 0% value times your tolerance setting times the percentage of your tolerance setting. So, for example, if we use 4 milliamps as a low range and 20 milliamps as upper range, our threshold for, and a 1% tolerance, our threshold for pass-fail would be around plus or minus 0.0016 milliamps. So to put this into context, if we're calibrating the URV at 1% tolerance, then our margin of error would be plus 19.9984 milliamps and 20.0016 milliamps. So any reading in between that would be acceptable as a pass. As mentioned before, if the unit passes the as-found test, no further action is necessary. However, if the unit does not pass the as-found test, the next step would be adjustment. So this is where the calibration portion comes in. So this process involves changing the URV and LRV parameters to match what is being read on the calibrator. So if our span is 2000 psi, we want the transmitter outputting 20 milliamps when the calibrator is reading 2000 psi, and 4 milliamps when it's reading 0. Following this adjustment, we then do the as-left calibration in a similar fashion. If the adjustments were done properly in the previous step, we would see the transmitter reacting more similarly to the calibrator. After the as-left process is finished, we then do a report generation. So report generation is very important to any kind of field instrumentation work, and it must contain certain parameters on there that will allow other people to understand the type of test performed, the instruments that were used, and the time that the tests were performed, as well as the results. So here's an example of a report that was generated using a Yokogawa FieldMate interface. So this shows the type of transmitter being tested, an EJX110A, the type of test, the pressure range that was involved in the test, the output range, and the tolerance. On the right, it shows you the date this process took place. It shows you the model of the calibrator and the serial number. And then in the bottom, it shows you the results of the as-found and as-left test. So as you can see here, the transmitter failed at 0 kPa. Its measured data was 2.58%, which is above the 1% tolerance that we had set. We then performed adjustments on the transmitter and then performed the as-left test. And you can see here, the results are much better. So I'm going to conclude the discussion of calibration with some of the Yokogawa equipment available. So one of this is the Yokogawa portable pressure calibrator, the CA700. This uses the same DP HARP series sensors as our EJA and EJX series transmitters. It is fully battery powered, and it is a 0.01% of reading for pressure accuracy. Another tool which was released in 2017. So since the release of the CA700 back in 2013, Yokogawa has gotten more demand to be able to calibrate larger and larger pressure ranges. And in response to this, we released the PM100 2300 PSI pressure module. So this is essentially I'd say three units in one package. And the reason I say that is because this allows you to offer range switching. So you have three different ranges built in: 7, 10, and 16 megapascals. And at any given point, you can choose which range you want to test if you prefer higher resolution at a certain pressure range. This maintains the same basic accuracy of the CA700, and it uses a data communication cable to connect to the unit. The next Yokogawa tool I'll go over is FieldMate. So FieldMate is kind of the glue in the whole process. FieldMate is a device configuration and management tool. It can be portable or operated via PC. It's essentially a management tool to connect to various types of field instrumentation, whether it be pressure transmitters, flow meters, temperature transmitters. It supports various protocols that are commonly used in the field, and it also allows you to connect to non-Yokogawa devices as well through the open DTM FDT framework. At the moment, we have two versions of FieldMate available, the Lite and the Full Function Edition. The Full Function Edition allows support for up to 500 devices, shows up to 10 parameters in the home screen, and currently has support available. Also mentioned earlier was that FieldMate supports the standard protocols that are seen in field instruments. So ISA 100, Modbus, Profibus, Brain, and HART. Here's a screenshot of one of the applications of FieldMate. So you can see here from the home screen the type of transmitter it's connected to, the device status, which indicates if there's one or more alarms on the unit, typical parameters that are being measured by the unit. So you can see that you are connected to a pressure transmitter. It's currently reading close to 0, and it's outputting about 4 milliamps, so it's trimmed properly on the low end. You also see the URV and LRV that the transmitter is set up for. Other features also include be able to read the tag and the vendor of the transmitter. Another feature of FieldMate is multi-protocol support. So that allows you to seamlessly change communication protocols that FieldMate is using depending on the type of transmitter you have connected. So this would essentially makes your field work more efficient and without having to restart the software or perform other actions that could slow down work. Here we have a view of the workflow for device installation. So some other features that are available are zero adjustment, loop check, and a one-click work report that generates a parameter list and alarm settings for a particular type of transmitter. Also released in 2017, we had FieldMate 3.03. So some of the new features in here involve the ability for the FieldMate to remotely connect to a CA700 and perform the same as found and as left and data logging calibration procedures as on the main unit. It allows you to perform its work in a central, easy-to-use platform. Other new features include the ability to trend data and monitor alarmless history. So going further into the 3.03 update, here is a basic diagram of how the interface is set up. So FieldMate utilizes a USB modem. Depending on the type of transmitter that's used, this could be either a USB to heart or a USB to brain modem. An external 24-volt DC power supply is powering the transmitter. And as I'll show you in the next diagram, this is actually coming from the loop power of the CA700. There's also a 250 ohm heart resistor or brain resistor that allows the FieldMate modem to generate the protocol from the 24 volts DC out. So here's the overall block diagram of the 3.03 update. So you see FieldMate connected to a CA700 via USB, and connected to a transmitter via USB to FieldMate modem. The CA700 then provides 24 volts DC out to the transmitter to power on the transmitter. The FieldMate modem then uses that 24 volt output to generate the heart or brain protocol. And finally, to close the loop is a pressure pump supplying pressure to both the transmitter and the CA700. Now with this complete setup, this extends the reach and versatility of FieldMate, allowing you to perform pressure calibration in addition to the other tasks it can do. So to summarize for FieldMate, so some of the features involve on-screen configuration guides and efficient device configuration. Also, support of device configuration of multiple vendors and leading industry standard communication protocols. Easy one-click report generation, and shared maintenance information with plant resource management. So some of the applications for this platform involve maintenance. So maintenance, commissioning of any kind of field equipment, recalibration or calibration and recalibration of field equipment as well. Flow measurement. So I'll give a brief summary of some of the points that were discussed today. So we started off with a discussion on pressure transmitters and the different types of ways that pressure is measured. So gauge, which uses atmospheric pressure at sea level as the reference. Absolute pressure, which uses perfect vacuum as a reference. And the differential, which takes difference of the high and low sides of the transmitter. And then we also talked about the three types of sensor technologies available in pressure transmitters. So capacitive, which outputs a change in capacitance in relation to applied stress. Piezoelectric, which utilizes a Wheatstone bridge. The Wheatstone bridge leg's change in resistance is proportional to the applied pressure. And finally, silicon resonant, which is what Yokogawa's pressure transmitter series use. These are composed of two H bridges, which resonate at 90 kilohertz. As the pressure is applied, one goes into compression and the other one goes into tension. And eventually, the frequency difference is amplified by the applied pressure. We then touched upon sensors and calibrators. So sensors are devices that output voltage, current, or resistance in proportion to measured phenomena such as temperature or pressure. Calibrators have the same features but take this one step further by being able to source these same signals to be able to check the health and validation of sensors. They're generally 3 to 4 times as accurate in their sensing technology. Then we touched upon calibration and verification. So verification is a subset of calibration. Verification involves checking the linearity of a transmitter across its different scaling points. If any of these tests fail verification, then calibration is then performed where the actual points are adjusted on the unit. Then we went more in depth into pressure calibration. So we went over as-found testing, which is the performance of the unit in inflated state, adjustment and trimming if the device failed, as-found testing, as-left testing, which is performed after the adjustment phase to make sure the adjustments were done properly, and then finally report generation, which allows the user to see the devices involved, the date and time the test took place, the make and model of the individual devices, and the results of the as-found and as-left tests. Lastly, we did a brief overview of the Yokogawa tools that are used for pressure transmitter calibration. So this involves the CA700 portable pressure calibrator, the PM100 high pressure module that extends the range of the CA700, and finally FieldMate, which is the device interaction software that combines all these pieces together and allows you to perform calibration work on one centralized unit. As a disclaimer, images within this presentation are from various sources unless otherwise noted. And with that, I'll hand it off to Elizabeth to go over any questions you may have.
Thank you, Ronit. We did get a few questions. We'll go ahead and address those now, and as we're going through them, as a reminder, you can continue to submit questions as we are reviewing these. Our first one is, how often do I need to perform calibration?
So that's a good question. So typically, Yokogawa EJA and EJX series pressure transmitters do not necessarily need periodic recalibration once they are delivered from the factory and trimmed for their specific applications. However, in general, calibration and or verification should be performed once a year on field equipment to ensure optimal performance.
Great. Our next one is, does the CA700 come with range switching?
The CA700 comes with 3 default ranges depending on the model code selected, with a maximum allowable pressure sensor range of 0 to 507 psi. Therefore, range switching to smaller ranges is not permissible. However, the PM100-E-5 pressure module that comes with the that's the pressure module for the CA700. That unit comes as default with 3 built-in ranges, so 0 to 7, 0 to 10, or 0 to 16 MPa, or 2300 psi.
Okay. We've got another one. Are there plans to go above 2300 psi?
We are planning on launching a higher pressure variant of the PM100, which will extend the range to 10,000 psi. More information will come on that in the next few months.
Okay. We have one more. How is sensor trimming performed?
So sensor trimming involves the actual calibration process. This is typically done using a communicator device set up for the same protocols as on the sensor. The trimming involves adjusting the URV and LRV so that the span is perfectly linear about the trimming range.
And thank you again, Ronit, for the presentation. Did you have anything else before we wrap up?
No, Elizabeth, I did not. Thank you, everybody, for attending, and I hope you enjoyed it and found it informative. If you have any questions, please, as Elizabeth said, please don't hesitate to contact me at my email address. And we'll be sending out a recording of this webinar as well as the slides in the next coming days.
Great. Thank you, everyone. See you next time.